Leaving behind descriptive statistics, we're now going to shift to something called inferential statistics. And please notice the label. I didn't say infernal statistics, I said inferential statistics. This is where statistics really gets interesting. Because what we're doing in descriptive statistics is simply summarizing, describing what we have. What we're doing in inferential statistics is, well, going beyond the information that we have to make a projection about what's true in all the rest of the world. Now, stop and think about that for a second. That's a lot of leverage to be able to talk to some people and reach conclusions that are true, we believe, for all people. What inferential statistics allows us to do is to test a drug on maybe 2,000, 3,000, 4,000 people and reach conclusions that we are fairly confident true for the billions of people that make up the planet. Now, that's profound. And if you read your history, that changed everything. Gone are the days of old when physicians would say, well, everybody's unique and individual. We have to see what works for each person individually. And now we've entered the era where we can make generalizations, we can base our understanding on science, because what we decide is true for some, we realize is likely true for all. What we're doing in inferential statistics then is a very simple process. We're starting with data, and we're making a projection from that sample of data to the population, that is, from what we have to what is beyond our own experience. This is a profound ability. It lets us deal with some and say something about all. And I'm being redundant here over and over again because this is the core idea. Once you get used to this, a lot of what confuses people in statistics simply evaporates. We're not simply talking about what we have, we're trying to leap from what we have and build a bridge to the whole rest of the world. From the sample to the population is the way we talk about this, usually technically. The two ways we build this bridge from the sample to the population: confidence intervals and p-values. We're going to talk our way through both of these sets of issues, but we're going to start by talking about confidence intervals. And the reason is, well, this is how inferential statistics are done in medicine. Pick up your favorite medical journal, look at a research-based article, and basically, if you don't understand confidence intervals, you don't understand the journal article. Because confidence intervals are the way that we do this, well, leap from the data to the population in medicine. Now, confidence intervals as a concept are fairly straightforward. It's simply realization that the exact number we have isn't reality, but reality is around the number. That is, the number we have is an approximation of reality, but not exactly reality. Pretty much we live our lives by confidence intervals, don't we? You say you're going to meet somebody at 8 o'clock, but as long as you come in, around 8 o'clock, maybe 5 minutes afterwards, you're still considered on time. Because again, we have a realization that reality is not some precise number, but it's around that particular number. You're out driving in your car. Posted speed limit says 55. You're driving along at 62 miles an hour. The police pull you over and give you a ticket. Most people are angry because, well, research published last year says most of us figure we get plus or minus 10 miles an hour around the speed limit. That is, if we're going along at 67 and the police give us a ticket, we figure we deserve that. If we're going at 62 and the police give us a ticket, we figure that's unfair. This is a sense, again, of what confidence intervals are. It's around that precise number. Now, what we're doing in confidence intervals, then, is a basic, simple trade-off. We get to give up that exact number, but we get to get a sense about what reality is inside of a range. It's a trade-off where we trade off precision for confidence, a precise number in which we are pretty sure isn't going to be real, for a range in which we figure reality likely is going to be. Again, the trade-off is from precision to confidence. Now, I know that seems a little abstract, so let's be very concrete. Suppose I give you all a test. You all get your scores back on the test, and I want to see how you all did on the test. But I don't have time to talk to everyone in the class. Instead, I go out and I randomly get scores from 6 students out of this much larger class. I now compute the mean for those 6 people. Add their scores together, divide by 6. I have the mean for those 6. The question simply is the mean for those 6 likely to be the mean for the class as a whole if I talk to everybody? Well, almost certainly not. But is it likely to be close, a good approximation, in the ballpark? Well, right there is exactly what we're doing. We talk about inferential statistics. We have a number that is close. We realize reality is likely around that number. Not exactly the number, but around that particular number. That's it, confidence interval. Now, it's not enough just to have a sense of the concept. We also have to do a little bit of calculation. The reason why we do a calculation, the reason why we have a few formulas here is, well, very pedestrian, to make sure that I, with the same information you have, get the same answer. The reason why we do a calculation is to make sure we consensually all arrive at the same interval as we're trying to get a sense of what the reality is based on the sample we have. But once again, understand what we're doing. Confidence intervals, we're taking the data from the sample and we're projecting to what reality is. A confidence interval, therefore, is your window on reality. Reality somewhere in the specified range. Reality is not this exact number, but it's around the number. The key lesson here is that your focus should not be on the numbers from the data. It ought to be on the projection of reality. Because as physicians, it's not the data, it's the reality that ought to be of most concern. The basic calculation you need for this section is the calculation of the confidence interval of the mean. The formula for the confidence interval of the mean is given here on the slide. It's x bar, the mean, plus or minus z, times quantity s divided by square root of n. That's really very basic. But to make sure you understand what we're talking about here, let me walk through the pieces. Make sure you understand what goes into this calculation of the confidence interval of the mean. So let's talk through what goes into this formula for the confidence interval of the mean. Well, first we start off with x bar, which is, of course, the mean itself. You know how to compute the mean. It's simply the arithmetic average. And this is the anchor point for the range that we're about to derive. Plus or minus, that means equidistant going above or below the mean. Again, the same amount above as we go below. Next comes z. We'll hop over that for a second. I'm going to focus on what's in the parentheses. What's in the parentheses is SE, or the standard error. This is the standard error. Now, if you had a choice, you think you would like this number to be large or small. Well, of course, small. Error is bad, so less error would be a good thing. You'd like this number to be as small as possible. Please note, two things go into the standard error. S, standard deviation, and n, the sample size. S and n make up the standard error. Note, not S and M, that's a different lecture. I said S and n, the standard deviation, and the sample size. Let's think about why these are involved in the standard error. Suppose I have two people doing research. Somebody has a sample of maybe 300. Somebody else has a sample of maybe 3,000. Who, in your opinion, has a better picture of what reality looks like? Sample 300 or sample 3,000? Well, of course, sample of 3,000. The larger the sample, the more information, the clearer our picture of what reality is. And so n, bang, goes on the bottom. Because as the sample size increases, the amount of information increases, our picture of reality gets better. As picture of reality gets better, error should go down. Let's now talk about S, the standard deviation. Let's walk you through two comparative hypotheticals to give you a sense of what we're talking about with the standard deviation. Suppose I give everyone in the class a test, and stunningly, everyone scores exactly the same. 75% for everybody, no exception. Everyone in the class gets 75%. I now sample 5 people at random and use those 5 people at random in order to represent the class as a whole. Do I get a good representation or a poor representation? Well, I get a perfect representation. Because if everybody has the same score, those 5 are literally as good as anybody. All right, here's the contrast. Once again, I give the class a test, but this time everybody scores all over the map, from 0% to 100% and everywhere in between. Once again, I sample 5 people and use those 5 to represent the class as a whole. This second time, do I get a good representation or poor representation? Well, I get a terrible representation, right? Because everybody's all over the map, and so the odds of getting strange or aberrant scores are relatively much higher. All right, here's what you just told me, translated. You just told me that the smaller the standard deviation, the less error, and the larger the standard deviation, the more error. And so bang, S, the standard deviation goes on top. Two things go into the standard error. S, smaller would be better, and N, larger would be better. Which one of these two is under my control? Which one of these two can I as a researcher do something about? Well, the answer, of course, is the sample size. This is why if you do any research at all, you're going to hear one theme all the time from a statistical consultant. Like a drumbeat, you hear the sample size, the sample size, the sample size. Why? Because this is literally your lever to reduce error. As the sample size increases, your picture reality gets better, and the error with which you're getting a measure of that reality goes down. Think about this in the extreme. When the sample size goes to infinity, I have no sample, I have reality. As the sample size increases, my error goes down. Two things go into the standard error. S, smaller is better, and N, larger is better. Okay, we have one more parameter to talk about in our equation. That is the Z that we skipped over before. Z stands for a Z-score or a standard score. Now let's pause for a moment and do a quick vocabulary check, shall we? What is S? The standard deviation, right. What is S divided by square root of N? The standard error. What is Z? The standard score, also known as a Z-score. The point of that little exercise is to point out to you that there's three standards. It's the second word that you have to pay attention to. If they give you on an exam question, for example, a standard error, do not divide it by the square root of N. It's already been done. If they give you a standard deviation, then you may well have to do that in order to solve the presented problem. Let's go back, though, and talk about a Z-score that is a standard score. A standard score is a score taken from a distribution that we, oh, you'll love this, we made it up. We were just sitting around drinking way too much beer one day, and we made this sucker up. We made it up to the following simple properties. First, mean equals 0, and standard deviation equal 1. Why do we give it these properties? Because it's easy to work with and useful to have this information. Here's what we get from a mean equal to 0. Well, when I look at the value of a score, I know immediately whether it's above or below the mean. If it's a positive number, clearly it's above the mean. If it's a negative number, clearly it's below the mean. I know instantaneously, therefore, positive or negative sign, whether I'm above or below the mean. Standard deviation equals 1. Well, that means I'm in standard deviation units. It means that I know instantaneously, upon getting the value, exactly how many standard deviations I am above or below the mean. Quite simply, if I have a Z-score of plus 1, how many standard deviations am I above the mean? That's obvious, 1, because Z-scores are giving me standard deviation units. If I have a Z-score of negative 1.8, how many standard deviations am I below the mean? 1.8. And please note, not about 1.8, exactly 1.8, because again, it's in standard deviation units. Okay, now let's make use of that. In any Z-score distribution, what percentage of the cases fall between a Z-score of plus 2 and minus 2? Well, that's easy. Like in any normal distribution, that would be 95.5%. 95.5% would be between a Z-score plus 2 and minus 2. But 95.5%. Isn't that 0.5 an annoying appendage? I don't want 95.5%. I want 95% exactly. So in order to get from 95.5 to 95% exactly, I simply have to tuck it in just a little bit from either side. Not all the way to plus or minus 2, but plus or minus 1.96 gives me exactly 95% of the cases. How do you know that's true? Because I'm telling you it is. I'm not going to do a proof for you. Just go with me on this. Okay. What percent of the cases in a Z-score distribution fall between a Z-score of plus 3 and minus 3? Well, that's going to be 99.7% of the cases, just like in any normal distribution. 99.7. Once again, isn't that 0.7 an annoying appendage? Well, let's get rid of that. Let's take it down to exactly 99%. So once again, we have to tuck it in a little bit from either side. Tuck it in how far? Plus or minus 2.58 gives us exactly 99% of the cases. So what? Well, So everything, because I now have the numbers I need in order to get the degree of confidence I wish to achieve. See, we have here the formula for a confidence interval. The standard error gives you, in some sense, the interval. It tells you how wide an area you have to look in order to get a sense of reality. Z is where we get the confidence. It's where we're going to insert the degree of certainty, that is, the degree of confidence we're going to have in my confidence interval. What do? I simply take the number I need in order to get the degree of confidence and insert it in to be Z. So Z is one of the following two numbers. If I want to have 95% confidence, Z equals 1.96. If I want to have 99% confidence, Z equals 2.58. That's it. Z is a simple binary switch. It's one of those two numbers depending on the degree of confidence you wish to have. Wait, I'll make it even easier. Because as you're whipping through your exam questions, without a lot of time available to you, you're not going to do a calculation using 1.96. That's too hard. Instead, you're going to use, 2. 2 is not exact, but it is, as we say, close enough for government work. So go ahead. It'll get you close enough to be able to get the right answer. And you're not going to use 2.58. That's too hard for 99%. You're going to use, well, not 3, but 2.5. And frankly, 2.6 would be a better number, but 2.5 will get you through your exam. So Z is a simple binary switch. It's one of these two numbers. 2, if you wish to have 95% confidence, or 2.5 if you wish to have 99% confidence. That's it. You now have everything you need before you to compute your very own confidence interval of the mean. Sometimes, as you're reading a research article or as you're reading an exam question, they won't give you the full confidence interval. Instead, they'll give you the mean and the standard error. The reason is you can then compute the confidence interval you decide is most appropriate. You can simply multiply the standard error times 2 if you want 95% confidence, or multiply the standard error times 2.5 if you want 99% confidence. They don't have to give you, please note, the entire confidence interval. All they have to give you is a mean and a standard error, and you can construct a confidence interval yourself. You know what? I have an idea. Let's actually do a confidence interval together, shall we? I don't know about you, but I always think it's fun to do a confidence interval, so let's do one together. We have data given that I've collected from a class several years ago. The mean was 67%. Standard deviation 8%, and I got that information not from the entire class, but from a sample of just 16 people from this much larger class. Using that information, we need to compute a 95% confidence interval. That's the problem before us. Well, we have to begin by remembering the formula for the confidence interval, which of course is the mean plus or minus Z times the standard error. The standard error being S divided by square root of n. In case you forgot the formula, there it is on the screen before you. All we need to do now is quite simply take the values presented, plug them into the formula, and derive the answer. So it's going to be 67 plus or minus, well, it's a 95% confidence interval, so that's 2 for the z-score. And then the standard error is, of course, S, that is 8, divided by the square root of n, which is the square root of 16. So let's see, the square root of 16 is 4. 8 divided by 4 is 2. 2 times 2 is 4. And there we have our 95% confidence interval, 67 plus or minus 4. 67 plus or minus 4, what does that mean? Simple. It means if I were to not simply talk to just these 16 people, but would look at the class as a whole, I would likely find the real mean for the class is somewhere between 71 and 63, somewhere inside that specified range. Notice once again, concretely, what's happened here. I've traded precision for confidence. I've given up the exact number, 67, in which from my sample I have 0% confidence that it represents total reality, and I've traded in for a range of 63 to 71 where I now have a 95% confidence. Okay, a few simple questions here. First, are you absolutely rock solid sure that the real mean is somewhere between 71 and 63? The answer, of course, is no, you're not. You're 95% sure, because that's what you bought with your z-score. If I do this 100 times, I'll be wrong 5 of those 100 times, but still, being right 95% of the time is pretty good odds. Second issue, I said the real mean is somewhere in the range of 71 to 63, which is correct. But come on, where is it most likely to be? The real mean is most likely to be what? Well, if you're thinking 67%, please toss out that answer because it's not correct. The real mean is somewhere between 71 and 63. More than that, I simply cannot say. The real mean is somewhere in that specified range. Don't think about that range as giving you a bell-shaped probability distribution. Think about it as giving you a flat probability distribution. So again, concretely, the real mean is just as likely to be 71 as it is 67, as it is 63. Somewhere in that range, and more than that, I cannot say. Having talked about what that range means, let's also now emphasize what that range does not tell us. This range does not mean that 95% of the class scored between 71 and 63. That would be the mean plus or minus 2 standard deviations, and I can't do that here. Why can't I do that? Because, please note, I don't even know what the mean is. I can't take the mean plus or minus 2 standard deviations because I don't know what the actual mean is. Yes, I have a mean from these 16 people, but I don't know the mean of the whole class. The best I can do for you is tell you it's between 71 and 63. Again, somewhere in that specified range, and that's it. What we're getting here is a sense of what the actual mean is. What we're not getting here is where people scored within the given class. This is inferential statistics, projecting from the data to the actual mean. It's not descriptive statistics, summarizing where people are in the class that we have. Okay, having talked about how we're going to calculate the confidence interval of the mean, let's now talk about how we're going to interpret confidence intervals should we see them. I'm going to take you away from medicine just for a moment and have you look at confidence intervals in a different context. Many years ago, there was a heated political contest in the United States, a presidential election year, in which George Bush was running against John Kerry for president. Not wanting to be left out, I conducted my very own public opinion poll prior to the election, trying to get a sense of who people supported for president. The results of the poll I'm going to reveal to you here today. People in my survey were given a choice to express their support for either George Bush or John Kerry. And the results of the poll are as follows. 44% of the people surveyed in this telephone survey said they supported Bush for president, whereas 49% of the people in the survey said they supported Kerry for president. Now, I got that information by talking to a sample of 247 people across the country. That's it. Not the whole country, not all the voters, just 247 people sampled in this telephone survey. And one other crucial number. You also see over here plus or minus 3%. That plus or minus 3% is an error of measurement. Error of measurement can mean a number of things in different contexts, but in this context, I want you to treat that as a 95% confidence interval. Again, it doesn't always mean that, but I want you to treat it in this context as a 95% confidence interval. Okay, with that in place, now a simple question. Could you walk into Kerry headquarters and tell him with 95% certainty he's leading in the poll? In short, is Kerry ahead, yes or no? The answer, of course, is no. And the reason is we don't just simply look at the data we have, 44% and 49%. We have to project from the data we collected to what's true of the whole country. Our projection as to what's true of the whole country is this plus or minus 3%. We must go and do the projection because what matters is not just what these 247 people say. We must build a bridge from that simple set of data to what's true for the whole country. Our best guess here is plus or minus 3%, which tells us that in reality, the support for Bush could be as low as 41% or as high as 47%. It tells us that in reality, the support for Kerry could be as high as 52% or as low as 46%. So it means they could be the same. And since they could be the same, they're not different. Here's a simple key for your keychain when handling statistics. When comparing confidence intervals, in general, any overlap means no difference. When you're comparing confidence intervals, if they overlap, then we can't feel sure that there's a difference, so we declare there is no difference. Now, the logic here is fairly straightforward, but very important. Reality, boom, is somewhere inside this range. Reality, boom, is somewhere inside this range. I don't know where inside the range reality is, but I know reality is inside that range. Well, if the two ranges do not overlap, I can then reach the logical conclusion that the realities are different. the two ranges do overlap, I can't reach that conclusion, and I'm stuck with the conservative position that there is no difference. Simple idea, but key for making simple interpretations on your exam. When comparing confidence intervals, especially confidence interval of the mean in this context, any overlap means no difference. With that idea in mind, let's go on and talk about a more medical example of this same information. You're presented here with a graphic that shows you the results of a clinical trial where we're comparing the efficacy of three separate antihypertensive agents called, all right, not very creatively, drug A, drug B, and drug C. This is the results at the end of a 6-month trial on medication. Now, all three of the groups on these drugs had the exact same blood pressures at the start of the clinical trial. All I need to do, therefore, to provide simplified presentation is present for you their average blood pressures at the end of 6 months on medication. We have the three drugs listed along the horizontal axis. The vertical axis is simply blood pressure, high being on the top and low being on the bottom. Well, you see for each of these drugs we have a little dot indicating the average, that is the mean blood pressure relative to the vertical axis. You also see for each of these drugs we have bars going above and below that little dot. These bars constitute the 95% confidence interval. So, using that information, here comes the question. Looking at the data presented in this graph, true or false? Drug A works better than drug B. Well, that's of course false. Why? Any overlap means no difference. Since A and B overlap, they are simply not different. True or false? Drug A works better than drug C. Well, that's true. You can see that drug A, the whole range is lower than the range of drug C, and so A lowers blood pressure further than drug C. And of course, B and C are not different at all because C is encapsulated within the range provided by drug B. A simple sentence to choose to summarize this data would be A and C are different and nothing else is. We're simply applying the rule we learned before, namely, any overlap means no difference. Now, I've been talking pretty exclusively till this point about a 95% confidence interval. Let's shift. Let's shift to talk about a 99% confidence interval. First question, is a 99% confidence interval going to be broader or narrower than a 95%? Broader or narrower? Well, the answer, of course, is broader. And here's why. First, I'm plugging into, for my z-score, 2.5 instead of 2. Because I'm using a larger number, clearly, by simple brute mathematics, my interval must be larger. But in case that doesn't resonate for the left side of your brain, let me try for the right-hand side. Suppose I go running out of the class here, and I go hide in one of the other rooms in this building. The job of the class is to come and find me and drag me back to finish lectures. Are you going to be more confident about finding me if you look for me in 3 rooms or in 5 rooms? Well, the answer, of course, you have more confidence if you look for me in 5 rooms, because more real estate gives you more confidence. A 99% confidence interval is therefore going to be broader than a 95% confidence interval. And again, that should make sense based on the principle I've been saying all along. What we're doing in confidence intervals is trading off precision, an exact number, for confidence. As our confidence interval increases in confidence, we're going to get broader, which is another way of saying we're going to be less precise. Confidence goes up, precision goes down. Let me draw in for you, in red here, the 99% confidence intervals. And now listen, here come some questions. Based on the data presented before you, true or false? At the 95% level, drug A works better than drug C. Well, that's true. It was before. It's still true now. At the 99% level, drug A works better than drug C. Well, that's false, because now at the 99% level, these intervals have overlap, and any overlap, therefore, means no difference. But by answering those two questions, yes, they're different than the 95% level. No, they're not different than the 99% level. Congratulations, you've just conducted a statistical test. No p-value will ever do more for you than you just did right there. You told me you're 95% sure they're different, but you're not 99% sure they're different. That's all we're doing with our confidence intervals. Giving ourselves a projection of reality, comparing the realities, and then being able to make a determination about whether they're different or not. Let's try to take you up a notch here. Look at what's presented here, and now I'm going to give you information you didn't have before. Listen up. The sample size for drug A, the sample size for drug B, the sample size for drug C are all the same. They're all, let's say, 300 people for each one of these groups. If all three of these groups have the same sample size, what can you now conclude about drug B? Well, what you should now be able to conclude is drug B has a very large, standard deviation. Because the mean is given, think about your formula, Z is a constant, N just became a constant. The only thing that I have to vary within the formula between each one of these bars is the standard deviation. If I have a wide interval, then B, drug B that is, must have a large standard deviation. Okay, large standard deviation. Here's a question. Is that a good property for a drug to have, large standard deviation? What that means concretely is different people respond differently to the drug. It has a heterogeneous response pattern. Different people are affected in different ways. Is that a good quality for a drug to have? Of course not. And so the final take-home question here is, you now have a choice. You can choose to prescribe for your patient drug A or drug B. Tell me which drug you prescribe and why. Well, we're going to prescribe drug A. We're going to prescribe drug A because it lowers blood pressure further. No, that's wrong. It does not lower blood pressure further, not the 95 or the 99% level. We're going to prescribe drug A because even though it lowers blood pressure the same as drug B, it has a more predictable response profile. It has a more homogeneous response pattern. In short, concretely, it has a smaller standard deviation. And since the means are the same, I'm going to go with the drug that has the more predictable response profile. What I've tried to do with this illustration is lead you step by step from 3 lines on the screen to a fairly sophisticated conclusion. Drug A is better, not because it lowers blood pressure more, but because it has a more predictable response profile. The last thing I want to talk to you about for confidence intervals has to do with confidence intervals and interpreting relative risk. Now, the issue here is not the computation. You will not be asked to compute a confidence interval for a relative risk. It's simply far too complex a calculation to do without a calculator. What you will be asked to do is make an interpretation, that is, decide whether a given relative risk value is significant or not. Let's focus you here on the top row of the presentation. We have a presented relative risk given to you at 1.57. Right beside that, we have a 95% confidence interval presented, ranging from 1.12 to 2.25. Now please note, that is a dash, not a minus sign. It means from this possible low, 1.12, to this possible high, 2.25. The question is this number presented, 1.57, statistically significant? And the answer is, yes it is. How do we know that? Well, the fact that 1.57 appears inside the presented confidence interval is trivial. It literally always will. If it doesn't, it's basically a typo. The critical value here is not 1.57, but the value at the bottom of your screen, the critical value is 1. If 1 falls inside that interval, then not significant. If 1.0 falls outside the interval, then it is significant. Why is 1 the critical value? Well, let's do a quick review here. We're computing a relative risk for what type of study? A cohort study, of course. What type of data do we get from a cohort study? We get incidence data. All right. Now suppose I have 2 incidence rates, incidence rate A and incidence rate B. Suppose the 2 incidence rates are identical. Incidence rate A equals incidence rate B. Well, when I do my relative risk calculation, that would be A divided by B, the return of that simple division would be the value 1. 1, therefore, means A and B are the same. Applying that to logic, if I want to demonstrate to you that A and B are different, one way I could do that is to demonstrate that the result of the relative risk is some number other than 1. If 1 is excluded as a possibility, therefore, I can make the reasonably safe assumption that there is a difference. With that in mind, let's go back and take a look at our table of data again. Presented a relative risk of 1.57. The 95% confidence interval, 1.12 to 2.25. as you traverse the number line from 1.12 to 2.25, do you go past the number 1? No, you do not. Therefore, this first row indicates statistical significance. 1 is outside the range, and therefore we have significance. Please note the relative risk number can now be interpreted because we know there's significance. The relative risk number is 1.57. It's a number over 1. And so we interpret this relative risk number by subtracting 1 from it and reading as a percentage. We would say that one of the groups has 57% more cases than the other group. Holding those ideas in mind, let's go down and look at the second row. Second row, we have 1.65. Is that a statistically significant relative risk? Well, you can't tell by looking at the relative risk number. You have to look at the presented 95% confidence interval. In this case, it ranges from a possible 0.89 to a possible 2.34. Well, as I traverse that presented number line, you can see that 1 falls squarely inside the range. Since 1 is inside the range, therefore not significant. Notice, even though the relative risk number here presented is larger than the previous one was significant, and this one is not significant. Because what matters here is not the value of the relative risk number, it's the interval presented as the 95% confidence interval. And remember the key, if 1 is in, not significant, 1 is inside the interval here, therefore not significant. I would make, on an exam question, no interpretation of the 1.65. I would simply say it's non-significant. Let's go down to the last row. A presented relative risk of 0.76. Significant? Well, once again, looking at the relative risk tells you nothing. Instead, look at the 95% confidence interval. Here you see we have an interval ranging from 0.56 to 0.93. Notice, once again, 1 is outside the interval. Because the issue here, folks, it's not about whether it's above 1 or below 1. It's about whether it's not 1. And since 1 falls outside that interval, this, therefore, is significant. Notice that the relative risk number, 0.76, falls below the number 1. Therefore, we would interpret this as reduced risk. We read this one of two ways. You can say, first, that one of the groups has 76% of the cases that the other group has, or more often, we say that one group has 24% fewer cases than the other one does, simply reading it by the difference between that number and 100%. The key in all of this is a very simple but crucial key. It's the number 1. I'll say it again. If 1 is in the interval, not significant. If 1 is outside the interval, is significant. And so reading down through the table, the first row, significant. The second row, non-significant. The third row, is significant. Now, I've been talking about how we're going to use confidence intervals to interpret relative risk. How might I use these same confidence intervals to deal with something like an odds ratio? How am I going to use this to deal with an odds ratio? Well, if I simply cross off the word relative risk here, and I scroll in the words odds ratio, everything I've just said over the last 7 minutes is exactly the same. How do I know whether an odds ratio from a case control study is statistically significant? Looking at the number doesn't tell me anything. Look at the 95% confidence interval. And again, it's all about the rule of 1. If 1 is in, not significant. If 1 is out, then we have significance. With that, we leave behind confidence intervals. Remembering, the confidence intervals are simply one way of estimating from our sample what the reality is out there in the population, projecting from the data we have an interval in which we believe we're going to be able to get a grip on, get a picture of what reality is. This is one way we do inferential statistics.